Alright, so in this video we're going to look at the reactions of haloalkanes to prepare for the chapter 15 test. I'm only going to look at the reactions at this video, not because they're the only things that are important from this topic, but I feel the rest of this topic you can go through yourself using the booklet. Whereas the reactions of haloalkanes, I don't know, I guess reactions are typically what students find hardest, but it's not. Because the other stuff is not important, okay? So make sure you're revising the whole chapter. Just watching this video is not even almost enough. So we're going to look at the hydrolysis of haloalkanes, which is only the reaction of haloalkanes that you need to know. And that word hydrolysis, hydro means water, and lysis means split. So you're going to use water to split up a haloalkane. I'm going to draw my haloalkane, just a typical haloalkane. So it's an alkane that has a halogen on it, so it's a haloalkane. And I'm going to be using water to split up this molecule. When we look at our haloalkane, the first thing I would always do when I'm doing the reactions is fill in my delta positive and my delta negative. Okay, your halogen is going to be more reactive than your carbon, giving you a delta positive carbon. Because you've got that delta positive carbon, haloalkanes are going to act as electrophiles. And it's this carbon that is always going to be attacked by a nucleophile. In this reaction, we're using water. So water is your reagent. Now, water is obviously typically H2O, but more specifically, from water, you can get the OH minus ion, and it's the OH minus ion that is your nucleophile in this case. So when I'm doing out my reaction mechanism, I've got my OH with a negative charge. I can start my curly arrow either at the lone pair or at the negative charge, but both electrons are coming from the oxygen. These electrons are going to be used to form a new bond between oxygen and carbon. In order to form a new bond with carbon, one of carbon's original bonds needs to break. And it's the bond between carbon and chlorine that is going to break. To show that that bond is breaking, I start my arrow on the bond. I'm going to end it there with the chlorine. Okay, so if I draw what happens next, I've got my 3 carbons. This carbon is no longer bonded to chlorine, but it is now bonded to oxygen. So I'm going to draw that there, and it's bonded to oxygen, which is bonded to the hydrogen. The 2 electrons that I have here on the oxygen are now the 2 electrons that are in this carbon-oxygen bond. So both of those electrons are coming from oxygen. Because both of the electrons are being supplied by oxygen, oxygen is essentially losing an electron to carbon. And because it's losing an electron, it loses that negative charge and just ends up being neutral. I'm also going to have a chlorine. The orange electrons that were in that carbon-chlorine bond both go with chlorine. One of those electrons always belonged to chlorine, but the other electron was from carbon. So chlorine is taking that electron with it. So it's getting its own electron back, but it's also getting carbon's electron. So it's gaining an electron, and it ends up with a negative charge. Carbon had a share of the orange electrons, but now it's got a share of these black electrons. It's sharing a different pair of electrons, but it's still ending up with the same number of electrons on each side. So the charge on carbon isn't going to change. You'll notice that you're starting off with something negatively charged and you're ending with something negatively charged. Okay, so if you're starting with something negative, you should be ending with something negative unless you've got something positive in there as well. Okay, and this is your full reaction mechanism. Your OH minus ions, which we get from water, attack the delta positive carbon. The carbon halogen bond breaks. You form an alcohol and you form Cl minus. So if I do that this time, if I use bromine instead, the reaction would be exactly the same. Delta positive, delta negative, attack the carbon, break the carbon halogen bond. I form a new bond between carbon and oxygen, and I form Br minus. Okay, I can draw the lone pair on the bromine, or I can leave it off. This will get me full marks. You have to include your partial positive, partial negative. Your arrows have to be nice and precise. So that's hydrolysis. You can often see hydrolysis with NaOH as your reagent. So NaOH, sodium hydroxide, is an alkali. It's aqueous, so you do have water present, and you've also got lots of OH minus ions. So they can write it as water, or they can write it as NaOH aqueous. Either way, you do still have water present, but having the NaOH will speed up the reaction. It's going to be exactly the same as what we had above. You substitute in your OH for your Cl, and you're going to form Cl minus. You could also then write that underneath as being NaCl. These are substitution reactions, and in each case you're substituting in a nucleophile, so it is going to be nucleophilic substitution. As well as using OH minus as a nucleophile, you can use lots of other things as nucleophiles. The reaction will be the same every time. So for example, if I have my haloalkane, sorry, I'm just drawing the same one each time, but it will be the same every time. But instead of using OH minus as a nucleophile, I'm using Cn minus as a nucleophile, and that negative charge is on the carbon, not on the nitrogen. I've got my delta positive and my delta negative. That carbon is always going to be attacked. So I attack the carbon, break that carbon-chlorine bond, and I get my Cn and I get my Cl minus. If I did another one, and this time I've got, I think this one came up in the exam questions not so long ago, I've got what's called a methoxy ion. Okay, that negative charge is on the oxygen. It's going to be the same every time. The carbon that's bonded to the halogen is going to be attacked by some form of nucleophile. When it's attacked, the carbon-halogen bond breaks. I'm losing the halogen. Instead, I've now got my OCH3. Okay, it's the oxygen that's attacking. So it's a carbon-oxygen bond that you're forming, and I form Br minus. Okay, so it's the same thing that's happening every single time. A nucleophile attacks the carbon, carbon-halogen bond breaks, you get substitution reaction, and you kick off the halogen with a negative charge. The other thing they ask you about this is they just ask you to compare the rate of hydrolysis between your different haloalkanes. So I've drawn 3 haloalkanes. They're all the same, apart from changing the halogen each time, going from chlorine to bromine to iodine. In these reactions, we can see that the carbon-halogen bond has to break, and it's this bond breaking that is the slowest step in the reaction, so is the rate-determining step. So in order to see which reaction will be fastest, I need to ask myself, which bond will break the quickest? The carbon-chlorine bond, the carbon-bromine bond, or the carbon-iodine bond? The carbon-iodine bond is the weakest. The carbon-chlorine bond is the strongest, because as you move down the group 7, the halogens are getting bigger. Because they're getting bigger, you don't get as good an overlap with the carbon. So carbon's up in period 2, and it forms stronger bonds with atoms that are a similar size. As you're moving down group 7, the atoms are getting bigger and bigger and bigger, and you don't get as a good an overlap between carbon and the bigger halogens. So carbon-iodine bonds are the weakest, carbon-chlorines are strongest. Actually, carbon-fluorine, they're both in the same period, they will be the strongest of all of the bonds. Because the carbon-iodine bonds are really weak, if you had iodine as your halogen and you were doing this reaction, the same reaction that we've seen time and time again, if we're doing that reaction, because this bond is so weak, it breaks so quickly, and that gives me a really, really quick reaction. If I compare that to my carbon-chlorine, which we've seen already, the reaction mechanism is going to be exactly the same, but because that bond is stronger, it will take longer for the carbon-chlorine bond to break than the carbon iodine bond, which slows down the reaction. So your iodine, haloalkanes with iodine are going to be more reactive than haloalkanes with a bromine or a chlorine, because that bond will break easier. Again, if you go and look in your booklet, there's a little experiment that you need to learn off. You need to know the reagents, silver nitrate, and you need to know the solvent, ethanol, so have a read through that as well. But this is the only mechanism that you need to know. It's the only reaction that you need to know in the haloalkanes. So as long as you're comfortable with hydrolysis, it should be okay. But again, don't just watch the video and assume that you know how to do it. Practice the questions that are in the booklet. I provided you with the answer booklet. It's on Teams. So make sure you're doing lots and lots of practice. You're not just sitting there reading or highlighting. You need to be practicing questions as you go along.